Welcome. Most of us have some interest in the universe, regardless of the profession. You could be an engineer, doctor, lawyer, but most of us wonder, what is this universe is? Is it finite? Is it infinite? It is going on forever? Did it start from nothing? Or was it there from very beginning, from eternity? So these questions most of us have, and we personally don't have time or don't have the ability to go through all the physics books. So what we do is we resort to believe whatever scientists tells us. But again, there is no one scientific opinion, So whom to believe? That's the whom to believe in physics is a big problem. If you look at the internet, you have all kinds of theories. There's a theory that says that there was a universe. Before the Big Bang, there was a universe. And that theory was put forward by none other than Roger Penrose. And he called it, what did he call? Conformal cyclic universe. Now, there is no evidence for another universe before the Big Bang. Absolutely none. But Roger Penrose is a Nobel Prize winner. He won the Nobel Prize in 2021 for his work in singularities in black holes. And he is a very well accepted, respected physicist for his work on singularities. But at the same time, he have this nonsensical theory which he calls conformal cosmic universe or something like that. So someone would say, okay, Roger Penrose is a Nobel Prize winner and, his theory has to be right and believe in it. But it is not accepted by anyone. So, and then another example is Carl Sagan. And Carl Sagan thoroughly believed that there's something called globular clusters. Globular clusters are millions of stars coming together. And Carl Sagan thoroughly believed that there could be intelligent aliens in these globular clusters. So he convinced NASA to send signals. But the problem is, in these globular clusters, the stars are very close by. Like if you take our solar system, after our solar system have planets. They're going in near, they're not going in circles, but these are not circles, but they're almost circles. They're ellipses, but they're almost circles. Now, if we had ellipses like this, then these planets will be bothering each other, and they will crash onto each other. One planet would go into the orbit of another planet. It would be a mess. But we have these nice concentric, almost concentric circles going around the sun. What this means is that after our solar system was born, no other star came near us. So we are lucky. But that's not going to be the situation here. There's going to be stars all over the place. The distance between stars are like distance between Sun and Neptune, something like that. And in this type of system, there's no way there could be stable planetary environment. Planets will be moving around and they get thrown out and they go into elliptical orbit. And if we had an elliptical orbit, instead of going like that, we would go like that, come back, and the world would be frozen by the time it come back near the sun. So under these conditions, you cannot have any type of meaningful life. And also these stars have only hydrogen and helium. You cannot have any life. So the bottom line is, he was wrong. Carl Sagan was wrong, but he was a very, very well respected scientist. Now, So we cannot really believe something just because they have done really good work in the past or have big fame. So we just can't believe in that. And then how about someone has a PhD, but someone has a PhD and qualifications and all that. But the problem is that I heard there are thousands of PhDs believe in intelligent creation theory. So someone having a PhD is not a good criteria. So how are we going to weed out the crackpot theories from good ones and see? So that is the main focus of this article: whom to believe in physics and what to believe. And unfortunately, I believe that you need to have some idea of fundamentals in physics. So that way you could match what you know, that mainstream science, and compare that with whatever the new theory that you read somewhere. And it's okay to read, it's okay to have open mind, but as long as you know whatever that theory is not in the mainstream, then you're fine. It could be proven right, it could be proven wrong, but it's not a widely accepted theory. And that way you will not get hoodwinked into believing in some crackpot theory. So let us look at some. So my idea is you should have some general understanding. So in this series we would look into Einstein's field equation. So there are 4 forces of nature. There's gravity, there's electromagnetic force, there's strong and weak nuclear force. We are going to discuss those forces very briefly. And we are going to discuss gravity. This is Einstein's field equation. We are not going to go into mathematics of it, just the conceptual part. It's going to be very easy. It's going to be very easy to understand Einstein's field equation conceptually. And then we are going to look at Big Bang theory, and then we would look at the Standard Model, etc. So let's start. Let's start with Einstein's field equation. And this is the Einstein field equation, or equations, I would say. And on this one, these R terms, these are called Ricci tensor, and this is Ricci scalar. These terms represent the curvature of the space and time, space-time. And this term represents this T is called the stress energy tensor, and this term represents the mass and energy. So this is the mass and energy of a system, and this is that mass and energy creating space-time curvature of the system. And what is this term? This is called the cosmological constant, and this is the metric tensor. So let us leave out this term for now. Let's forget about it for now. So this side, the right hand side, has mass and energy, and left hand side has curvature. So the mass and energy curves space-time. And this equation without this cosmological constant was a dynamic equation. It gave a universe that is either expanding or contracting, and it was not a static universe. So Einstein did not like it, so he added a new term, cosmological constant. But then later, people found that you don't really need that, so they got rid of it. But again, experimental evidence suggested that there is a cosmological constant, but with a different sign. I don't want to go into too much details here. So this is what you need to know. In Einstein equation, you have the mass, or the stress and energy and mass, and the other side you have the curvature. And I like to talk a little bit about these tensors. This is the Ricci tensor. What is a tensor? Tensor is a bunch of vectors. And what is a vector? Vector has a direction and a value. Now this is a vector. A rocket is going towards Sirius. A rocket is going towards Sirius, star Sirius. And it has a velocity and it has a direction. And there are two people, A and B. And B measures the rocket's velocity and its direction. And he comes up and says it's going towards Sirius. And he has a coordinate system. B has a certain coordinate system. And A also have a coordinate system different than B. And he measures, and he also comes up with the calculation. He also comes up with and say that that rocket ship is going towards Sirius, not Vega. So this rocket ship going towards Sirius is not going to depend upon someone's coordinate system. He could have any coordinate system. B and A could have any coordinate system. It doesn't matter. This rocket is going to Sirius. Period. So these vectors are not dependent upon coordinate systems. And I told that the tensors are a bunch of vectors. That's it. Tensors are a bunch of vectors. And they are arranged in a certain manner, like the stress tensor or Riemann tensor. All these are arranged in a certain manner, but yet they are a bunch of vectors. And if a tensor is just a bundle of vectors, then if a vector is an invariant or not dependent upon coordinate system, then tensors also should be invariant and should not depend on coordinate system. So tensors are invariant, have nothing to do with coordinate system. Their value should come the same which coordinate system you use. So this is the conceptual part of general relativity. You have mass or the stress and mass and energy on one side, and that's a tensor, and the other side you have space-time curvature. And next we will look into Big Bang theory a little bit and standard model, and then we will discuss general outline, whom to believe and what to believe. Thank you very much for listening.